Good morning, afternoon, or evening, everybody. Welcome to the Encore presentation for the Remote Sensing Derived Environmental Indicators for Decision-Making webinar. This is your host, Jennifer Brennan. While everybody is logging in here, you do see the two optional polls at the bottom of the page, and we appreciate your feedback on these polls. I've got 10 a.m. Eastern Time, so what we're going to do now is get started. What I'd like to do first is go over a few housekeeping items related to this webinar. To ensure the best audio experience, the conference has been placed in silent mode. However, if you have any questions or if you have any issues, what I'd like for you to do is enter those into the Q&A pod, and you'll find that located on the lower right-hand side of your screen. And this works like a chat. Excuse me. This webinar is being recorded and will be posted both to our online Adobe Connect catalog as well as to our NASA Earthdata YouTube channel within a couple of days of completion. And I do plan to provide the URL to all of you at the end. All presentation files will also be available for download at the end of the webinar. As far as timing is concerned, this webinar is 1 hour long. We've allocated 45 minutes to the presentation and live demonstration with an additional 15 minutes for the question and answer period. After our speaker has finished his presentation, we will then move to the final set of polling questions. And then from there, we will transition directly to the Q&A period. You will have an opportunity to ask your questions throughout all portions of the webinar with the exception of the demo portion by using the Q&A pod. And again, this works like a chat. Due to the large number of participants, questions will not be answered using the raising hand function. It has been disabled. And then just one final note, depending upon the volume of questions that we receive, we will extend the Q&A period an additional 15 minutes to 11:15 a.m. Eastern Time for those of you who may wish to stay on the line. What I'd like to do now is move next to the agenda. Let me pull that up for everybody here. During the first half of the webinar, our speaker will provide an overview of NASA's Socioeconomic Data and Application Center, or SEDAC. And then he'll describe what environmental indicators are and further explain how satellite data fit in. During the second half of the webinar, we will delve into the NASA SEDAC experience developing and disseminating satellite-derived indicators, and we'll also explore some of these data sets using the SEDAC map viewer. Finally, our speaker will discuss impacts of these environmental indicator data and future directions. With that, it is my pleasure to introduce our speaker today, Dr. Alex Desherbinen, who is the Deputy Manager at NASA SEDAC. Alex?
Thank you so much, Jennifer, and it's a real pleasure to be with everybody this morning or in whatever time zone you're at. At this time, I am waiting for the presenter. There we go. I'm going to start by just doing a little introduction of SEDAC and then moving through into the rest of the presentation. Some of you may not be as familiar with SEDAC. So we're the NASA Socioeconomic Data and Application Center. We're one of 12 NASA distributed archive centers. We're based here at Columbia University since 1998. We're at the Lamont campus, which is just outside of New York City. And you can see the smiling faces in the lower right. These are the staff that we have of natural scientists, GIS and remote sensing specialists, data management experts, and programmers and systems engineers. The main purpose of SEDAC is to provide the ground level context for NASA's remote sensing data, and our focus is on the human dimensions of environmental change. We have a very big emphasis on data integration, particularly integration of socioeconomic data with remote sensing data. And we provide direct support to scientists and applied operational users, decision makers, and policy communities. And we have very strong links to the geospatial data community. So SEDAC's interest in satellite-derived indicators has really, I would say it's about a decade-long interest. I'll be showing later some data products that we produce that integrate remote sensing data into sort of deliverable or disseminated data sets. But our interest in developing indicators, what we call level 4 products, is really stems from the fact that we recognize that policy audiences need sometimes highly processed data to make decisions with. And so you can think of the NASA sort of hierarchy of data, level 0 being raw instrument data, which are digital numbers, and then level 1 being geolocated and calibrated data, level 2 being an actual geophysical data product. You think of net primary productivity or NDVI or other products. And then level 3 are composites of the level 2 products. And finally, you have level 4, which are essentially model-derived data products that can be used in a number of different ways. And in this particular context, we're talking about data products that serve decision-making needs. This work also builds on 2 decades of experience working with Yale University on environmental indicators at the country level, the ESI, which is the Environmental Sustainability Index, and the EPI, the Environmental Performance Index, and you'll hear more about that later. And then we had a NASA ROSES project from 2009 to 2011, and I'll be discussing that a little bit more as well. That makes up a segment of my presentation. So what are environmental indicators and where do satellite data come in? Most of you are familiar with some high-level indicator products such as gross domestic product, which is a measure of the economic performance of countries, consumer price index, which is a measure of inflation in the United States, the Dow Jones Industrial Average, things like the Human Development Index that UNEP produces, or UNDP, and the Air Quality Index in the U.S., which can be very useful for people who have health or issues that may want to know what the air quality is on any given day before they go outside. So Yale and Season at Columbia University have developed indicators since 2000, or our first release was ESI in 2000, which are intended to serve as a counterweight to GDP and provide an evidence base for decision making in the environmental realm, much as GDP provides an evidence base in the economic realm. So indicators are born out of a recognition that policymaking needs to be data-driven, science-based, analytically rigorous, outcome-oriented, and a strong focus on change over time. And they speak to this maxim of what gets measured matters. And up until we started working in this terrain in the late 90s and early parts of this new millennium, we really had no measures that could be used by decision makers to guide sort of high-level policy making. We've broken down the purpose of indicators into 5 Ds, words that begin with the letter D. So the first is to describe the situation. They reduce complexity in policy-relevant ways. They're not necessarily tied to any policy target. And they answer the question, what's happening? If your child came home with this report card, you'd say, well, these are synthetic indicators, as it were, of a series of assignments that they've either succeeded at passing in or didn't pass in or failed at. And you guys say, well, you need help with Spanish or English or that kind of thing. So they can kind of point your attention to areas in need of greater attention. They also are useful for diagnosing situations. So it's possible to explore relationships between different phenomena, to explore competing trends, and to dig into anomalies. Indicators help policymakers and society as a whole deliberate and enter into a dialogue about what kind of future they want to have. They ground the discussion in empirical reality, and they help set up goalposts, which relates to the next D, which is for drive and driving action. And basically, if you know where you want to go, indicators can help you get there. They can help to hold decision makers and managers accountable, and they reward progress and can punish inaction where that needs to happen. And finally, indicators help us to discover patterns that we didn't know were there. Who are the leaders? Who are the laggards? Who are the best and worst? What are the best and worst practices? What makes one country, say Malaysia, perform better than Thailand when they both experience a similar economic boom in the 1990s? You can ask a number of these sorts of questions. They also help with targeting of resources. Some of the things we've learned from the EPI are that country-level indicators and indices can help set up a competitive dynamic among peer groups. So the Scandinavian countries typically compare themselves to their neighbors. In Asia, we found that many of the countries, such as Korea and Japan, Korea will naturally look to Japan as its sort of rival and will seek to improve its performance relative to Japan in different areas. Decision makers are interested in pressure and impact measures and also the state measures. If you think of the driving force, pressure, state, impact response framework, which OECD developed, DPSIR, and so they really want to know what outcomes are and how they're impacting human health and other factors. In addition, we found that indicators are most successful when they have the following characteristics, and this is really based on the larger literature, but also a report we produced with Yale in 2013, kind of assessing our experience with indicator development. So indicators are best when they're credible and they come from highly reputable sources, and decision makers feel they're of high technical quality. They're also really well received when they're salient and they meet the needs of the sort of issue of the day that decision makers are facing. We'll see in a little bit our air quality indicators from remote sensing have really resonated very heavily in East Asia and in India, where air quality is often a very big public policy issue. And legitimacy is also important. Do you have the necessary buy-in from the communities and stakeholders that might be guided by these indicators? So one of the benefits of satellite data are that they can fill the gaps that we have in situ monitoring networks. These are the ground-based monitoring networks for a whole host of things like air and water quality. Satellite data provide wall-to-wall coverage and consistent time series. Satellite data are not dependent on the vicissitudes of funding or political situations in countries that are being monitored. So if there's civil unrest or an economic downturn in a country that causes their environmental monitoring networks to be offline for a period, the satellite data are still out there collecting the data. And they can measure environmental changes and conditions in really hard to reach areas like the deepest parts of the Amazon. So I'm going to, for the next section, talk about the NASA ROSES project. And for those of you really who want to delve into this topic in more detail, I suggest downloading and reading this free online journal article that covers the highlights and the results of this NASA ROSES project in more detail than I'm able to do so today. The purpose of the project was to answer the question, can satellite data be successfully applied for development of scientifically robust environmental indicators? The work was conducted in 2009 to 2011, but the actual findings have continued to inform our work here at SEDAC for a while. The project team based at CSUN was Mark Levy, our deputy director, myself as a co-PI, and Melanding Jaita. And Battelle Memorial Institute also played a critical role with Erica Zell and Stephanie Weber as co-Is on this. The advisory group was composed of representatives from the World Bank, EPA, and Millennium Challenge Corporation, which is an aid-giving arm of the U.S. government. And they rely very heavily on indicators. Countries need to meet certain criteria and exceed the median for all least developed countries on different criteria. And the number of the indicators we develop for them are related to environment and sort of child health issues. So they were very interested in, all three of these stakeholders were very interested in the potential of remote sensing to inform their development and environmental decision making. We also had scientists from NASA, NOAA, and a number of universities, both in the U.S. and overseas. We focused on three areas: air quality, coastal water quality, and biomass burning. We had 7 feasibility criteria. First of all, the indicators needed to be accurate. They needed to have a large spatial coverage and extent. preferably a reasonably high spatial resolution to be able to detect subnational differences in the environmental parameters. They needed to have high temporal resolution, relatively frequent repeat periods in the language of remote sensing. They needed to be timely and accessible. In other words, an indicator that takes a year or two to produce is not really useful for timely decision making. There needed to be transparency and trust in the methodologies that were used, and the resource requirements needed to be reasonable. And again, the question was, could these environmental indicators support decision-making by these key stakeholders? So as I mentioned, the first area was ambient air quality. Our focus was really on human health exposure to ambient air pollution. We looked at two areas. One was fine particulate matter. These are what are called PM 2.5. These are particulate matter of 2.5 microns or smaller, and these are contrasted to, say, particulate matter of 10 microns or PM10, which is coarser particulates. These particulates lodge deep into the lung and cause a lot of health issues and potentially cancer with sufficient exposure. Nitrogen dioxide is also important health indicator and can be important for things like asthma and breathing difficulties, bronchitis. Currently, these are measured, or at the time they're measured primarily by ground stations in simulated air quality models, and there were many gaps and inconsistencies throughout the world. You can see in the lower left, the global in situ monitoring network looks fairly complete, but there's regions where there's just not much coverage at all in Asia and Africa. And in the U.S., it's a much denser network of PM 2.5 ground monitoring networks. We had the research community had explored the relationship between the satellite-derived aerosol optical depth measurements, which is on the x-axis in the chart on the lower right, and the ground-based measurements of daily PM 2.5, and found a very high correlation. So this is what sort of triggered the interest in using satellite data to fill in some of those gaps. I will just say up front that it's very important to have the ground-based data for validation. So remote sensing in and of itself is not enough. You do need these ground-based measurements in order to validate the satellite-derived metrics. So what we wanted to do was highlight the relative exposure and potential health impacts of air pollution by country. It's more of a high-level communication tool rather than a day-to-day air quality management tool. It's not going to tell you where your air pollution sources are coming from, it will not support ground control or pollution control measures necessarily, but it does help decision makers identify where the worst affected areas are, and hopefully triggers deeper analysis of what's going on the ground. So first of all, to calculate the indicators at country or subnational administrative unit level, we took pollutant data. These are column measurements of aerosol optical depth. So this is essentially how much bad stuff you have in the air viewed from space. It's run through a model to be able to understand what the likely concentrations are at ground level. So remember, we're looking from space. We have to take this column measurement and essentially translate to what people are breathing on the ground. Once we have that, we population weight it because we want to know if air pollution is higher in urbanized areas. We want to know that in fact a high proportion of the population in any administrative unit is really badly affected by this bad air quality in those urban areas. And then we come up with average annual population pollutant levels in different administrative units. So this is the kind of input data, which is gridded. You'll see this line across roughly 60 degrees north, which represents the limits of a retrieval on aerosol optical depth data from MODIS and MISER. It's run through the GEOS-Chem model by a group at Dalhousie University. And they've been refining this, and I'll describe some later products that they produce later in my presentation. Then we took SEDAC's Global Rural Urban Mapping Project, or GRUMP version 1 population grid, and we use that to weight the 1 kilometer aerosol optical depth data, or rather the PM 2.5 model data, to come up with population-weighted measures. And this, for instance, is the country-level metric that we derived. China, you can see, has roughly 5 times the WHO recommended levels of 10 micrograms per cubic meter. Other countries in India, Pakistan, much of the Middle East also has very high levels. And remember this, or I should state that this metric also removes crustal material. So to the extent possible, they remove the effect of dust storms in these very arid regions. And so it's really what we consider anthropogenic emissions that they're measuring, or concentrations. At the subnational level, what you can see is there's a lot of differences. So if you look at China, the northeastern region is really the most heavily polluted, whereas the western regions have relatively better levels of air quality. You know, in the Ganges basin, we see also very high concentrations of PM 2.5. And then you can do the same analysis for urban areas, looking at the annual or mean concentration over a period of time. We were told by health experts that it's perfectly appropriate to look at annual average concentrations because it does matter from a health perspective. You can then do measures such as this to look at the percentage of the world's population affected by different concentrations. So if you look at concentrations of above 40 micrograms per cubic meter, which is 4 times the World Health Organization benchmark level, about 25% of the world's population is in that 40 micrograms and above. About half of the world's population is at roughly 27 micrograms per cubic meter and above. And then you can look at bands of exposed populations by particulate matter levels. So this is above 35 micrograms per cubic meter. This is from 19 to 35 micrograms per cubic meter, and you begin to see parts of Europe and Central America and South America show up. And then from 11 to 19 micrograms per cubic meter, you have much larger areas that are populations that are exposed. So that was the biomass, the air quality indicator, and I'll come back to some of the kind of advisory group responses to that indicator at the end of this segment. So the next indicator was to do with coastal water quality, and one of the things that is different from air quality is ambient concentrations are not so important for coastal water quality. What really matters is the trend in the concentrations, because we know that certain regions of the world are just going to have higher concentrations, like off the coast here of parts of Indonesia or China. There are just sometimes naturally high concentrations of chlorophyll A. Now, chlorophyll A is what you're measuring here. It's basically derived from ocean color. It's related to eutrophication of water bodies and harmful algal blooms. And our interest and what we're really looking for is what kind of trends are there, and might those be associated with changes in urbanization or agricultural production, particularly nitrogen and phosphorus runoff coming from major rivers into the oceans, and can we detect trends that are happening in some of these coastal areas. We had some pilot work with a colleague here, Ajit Subramaniam, at Lamont Doherty Earth Observatory, and we looked initially just at annual average chlorophyll A measures, and we looked at the trends in those measures. Those data are being disseminated now by SEDAC. In our improved version for this project, what we did is we downloaded the CWIF data, we converted it to GIS formats, we clipped the data to the exclusive economic zones of each country because we're really interested in what's going on and we want to identify the patterns by country because, again, we're trying to tie this to country-level performance. We dropped missing data cells, especially their cloud cover and other issues that would affect the availability of data for any given month. We exported the grids to SPSS, which is a statistical processing software. We ran a regression of the chlorophyll A concentrations against the year with month dummies because we wanted to kind of account for seasonal variability, which is very high in the coastal zone. And then we exported the statistical data back out to a points shape file, converted that to grid so that we could map the data, and we only mapped those areas where there's a statistically significant trend in the coastal zone. So these are some example outputs. One of the things that's interesting to note is that at least during this particular time period, from 1997 to 2007, there was a statistically significant negative trend in the chlorophyll A concentrations in the Mississippi Delta region. But if you go along the coast to the coast of Texas, you see slightly positive trends in those areas. In Brazil, a little bit east of Rio de Janeiro, for some reason there was a positive trend in this region, and honestly we were not able to dig deeper in terms of what might be going on in these areas. We saw a positive trend in the Sea of Azov, which is part of the Black Sea, and that could be related to pollutants coming out of the Volga River. The Mediterranean had relatively stable levels, but some positive trends. Then we saw some positive trends, but very minor positive trends in the Bohai Sea, which is off the coast of China. We were really expecting to see much more intense changes in the China coastline owing to the levels of urbanization there, and we really don't have a strong explanation for why those trends did not materialize in the way we expected. So the next area that we looked at was biomass burning, and our main focus was on CO2 emissions. Land use emissions account for roughly 20 to 30% of global carbon emissions, and fires contribute a high percentage of those emissions. We were less directly concerned about health impacts because we felt we'd already captured that with the air quality metric. And we knew that fires impact some ecosystems negatively, and you could filter the results to look at, say, boreal ecosystems or things like that, but it's relatively difficult to assess the ecosystem impacts because we were told by experts in fire ecology that sometimes it's very necessary for fires to burn in certain ecosystems, certain forest ecosystems. So we chose to focus on climate impacts. We at first looked at the extent of burn scars, but they tend to exaggerate the sort of impact of fires, particularly in dryland and grassland areas of Africa. We had input from the advisory group, and they basically recommended that we use this GFED Global Fire Emissions Database version 3. So this is just a picture of the sort of spatial extent of burning in Africa, and you can see that it's very heavily concentrated in rangeland areas where fire is relatively frequent. The GFED3 is a time series emissions database. At that time, we now have a version 4, and I'll describe that a little later. But at that time, the database extended from 1997 to 2009 in monthly time steps. So we summarized the data on a half-degree grid. The data are originally derived from MODIS, burned area, and active fire data. And about 90% of global burned area at that time was mapped. Since 2000 is really the MODIS era. Before that, they used some combination of other sensors to measure burned areas. They do divide up the fires into different fire types. Our main focus was on forest or deforestation and degradation fires, forest fires, woodland fires, and peatland fires. We, at that time, omitted savanna and agriculture, partly because of the low net emissions from those sectors, and also because, so they're low net emissions because each year they may burn a certain area, but they grow back very quickly. So on an annual cycle, the net emissions is relatively low. We created annual grids, and we used R, a statistical software, to produce cluster maps, which I'll show in a moment. And then we also used MATLAB, and we produced total trend in emissions per NPP, that is, per net primary productivity by country. The data were regridded at 2.5 minutes for this country-level metric. This is the cluster map I mentioned, which really describes the sort of intensity and frequency of fires. And so a lot of Africa is very subject to fires and fairly frequent and intense fires. Parts of Malaysia and Southeast Asia are also very heavily impacted by fires, as are the boreal zones. We looked at annual emissions. This is just average annual emissions from 1997 to 2009, and you see boreal countries like Canada and Russia show up very highly, but also some of those parts of Africa and the Amazon, Brazil, show up as having very high emissions. These are average annual emissions by country, and basically Sudan during this time period had annual average emissions of around 89 million metric tons per year. Russia came in at 81 million metric tons per year. U.S. is around 13 with about 15 million metric tons per year, and Indonesia was ranked 70th at 24. We were interested in Indonesia partly because the peat fires that they had, especially during the El Nino year in 1997-98, were very, generated a lot of emissions. So the trends in emissions, we looked at the trends. We tried to discern whether there were any positive or negative trends that were statistically significant, and frankly, only a few countries had. Most of the green ones show negative trends, and then Angola, for some reason, had a very strong positive trend, as did Ukraine and Turkmenistan. We found that the trend data were less kind of interpretable, and partly because they're so influenced by climatic factors. So in terms of the advisory group feedback, what we found was that they found that biomass burning and water quality had slightly higher marks than air quality for scientific rigor. In terms of policy relevance, they found there was about 25 to 30% of respondents who rated all indicators as highly relevant, so a strong sort of positive sign that these were generally considered to be very relevant from a policy perspective, and a call for administrative and urban level indicators, because those are the units at which decision-making takes place and policymakers have influence. Almost all the respondents rated the three indicators as ready or nearly ready for use. There were differing perceptions on readiness for use between scientists and policymakers. And one of the things we discovered in this process is that scientists tended to think of indicators as being metrics of cause and effect, and they wanted to talk about it in terms of robustness and uncertainty. So their thinking on indicators and their interpretation of what an indicator represents is really more influenced by the scientific method and trying to understand cause and effect, and less by sort of the need to describe the situation in general terms, and so that policymakers could make decisions. So there were different interpretations of what indicators mean across the two communities. So I'm going to now turn briefly to some of the SEDAC derived data products that have either inputs of satellite data or are derived wholly from satellite data. These are some of the data products that integrate remote sensing, and they include the human appropriation and net primary productivity, which is based on NPP data from ABHRR long-term time series. The human footprint data set and Last of the Wild, which has nighttime lights data included. We've done data products such as the low elevation coastal zone, which measure populations in those in areas in each country in those low elevation areas, and that's using shuttle radar topography mission data. This is a one-time mission by NASA to collect radar topography. PLACE, which is the population landscape and climate estimates, which uses a variety of satellite inputs to measure population by country in different climate zones, biomes, and elevation categories. Anthropogenic biomes, which is produced by Earl Ellis at University of Maryland, Baltimore, and looks at, takes a number of satellite-derived inputs to generate a land cover map. And Global Grid of Probabilities of Urban Expansion, which was developed by Karen Cito and her team at Yale University, that takes our data on population density and combines it with MODIS urban extents to measure propensity of likely urbanization in the future. So now, at the current time, we currently disseminate these 5 data sets that are entirely based on satellite data that are processed in various ways. The ones that I'll have examples of each of these, so I'll describe them as I go through the presentation. And then there are some forthcoming data sets like nitrogen dioxide grids, a forthcoming particulate matter PM 2.5 grid that is using a slightly more robust model and has a longer extended time series. We'll be producing country and city level indicators alongside those grids so that people can just grab, what's going on in Beijing? How has air quality changed in that particular city over time? The same we'll be doing for global fire emissions indicators, and those data are from GFED4, as I mentioned, and we'll be doing country-level indicators. This is that sort of first-generation coastal chlorophyll product, which is available at the URL you'll see at the bottom of the screen. Some of the patterns I already described to you earlier in the NASA ROSES project description. This is the PM 2.5 grids and a snapshot for 2001 to 2010, a sort of decadal snapshot, and you see the very high concentrations in India and China, and parts of Africa. This is a trend measure that shows you the trend in those particulate matter concentrations across different parts of the world. That the positive trends are, or the worsening air quality is in the red areas. And then you can take these same data at a country level, as we did for the Environmental Performance Index, and look at trends and concentrations. So this is the trend for China and India at the top, where you see a worsening of particulate matter conditions, and the rest of the countries are sort of hovering around that WHO level of concentration, with some countries like the U.S. declining over that time period. This is the trend in the proportion of the population exposed to the worst particulate matter concentrations of 25 micrograms per cubic meter and above. And again, China and India are sort of see a increase in the populations exposed. The NO2 grids, which are about to be released soon, this is a picture for 1996 through 1998. So the first time period, see much of the eastern United States very heavily polluted, much of Europe, and eastern China looks maybe less concentrated in terms of its pollution level. If you look at the latter time period from 2010 to 2012, the U.S. improves, so does parts of Europe, and then China gets much worse. This is a land surface temperature grid that's based on MODIS data as an input for the next product, which I'll be describing. But one of the advantages is this is GIS ready and can be used for a whole host of purposes. Basically it represents something like the peak temperatures during a 40-day period of the worst summertime temperatures in both the northern and southern hemispheres. What we did is we used that grid of land surface temperature for both daytime and nighttime land surface temperature. And what we ran it through a process where we took the urban extents from Global Rural Urban Mapping Project and looked at the temperatures within, say, the large urban extent in the northeast corridor of the U.S. and the 10 kilometers around to see what the temperature differences are. This is Madrid, for instance, and parts of eastern China. And what you see is the orange areas are generally showing nighttime temperatures of 1 to 2 degrees warmer than the surrounding areas. This is use of satellite data from Global Forest Watch and Matthew Hansen at University of Maryland to measure deforestation by country. The map in the upper right-hand corner, white areas have low scores on forest cover, which means they're declining. Their forest cover is declining very steeply. And the blue or green countries have high scores, and that means they're doing a better job of conserving their forests. This is the biomass burning metric that I mentioned earlier from GFED4. This is the area, and these are kind of country trends. And as I mentioned, these are heavily influenced by climatic patterns. And so you see the ups and downs by year, and you see the trend line in the bottom right that sort of uncovers a downward trend for the Congo and a sort of stable trend for Brazil. At this point, I'm going to switch to the presentation of our map viewer very briefly before I come back to sort of describe the impact of these indicators. So very briefly, this is the new SEDAC map viewer, which has a 4-panel view. So all 4 maps kind of move in harmony here as you move from one place to the next around the world. You can obviously pan and zoom and do all the things you normally do. Let me go over to the Northeast United States, where some of our listeners may be from. And what you see here is the anthropogenic biomes, but I want to swap that out with a layer that describes summer, urban, nighttime, urban heat island. I'll change this one in the lower right to coastal water quality and add that in. And what you see then is the kind of urban difference in nighttime temperatures of major cities in the U.S. You also have particulate matter in the upper right-hand corner. And I'll just go back out and do, I'm sorry, I didn't realize that that's what that icon did, so I apologize for that. You can also pull up the, so this is the area around China, and you see the very high particulate matter, and also some trends in the coastal water quality. And you can pull up the legend by hitting the legend button and look at what the particulate matter levels are there, or in this case, what the temperature differences are in those urban areas. This is a very brief sort of view of that, so I'll switch back to the presentation and welcome you to play more with that mapping tool at after the presentation. So moving along, I want to just describe very briefly the impacts of this work and then future directions. So I'll be talking about how the indicators have been used, what their policy impacts have been, be talking a bit about the SDGs, and one of the questions I have for you is what new products might be developed in the future. So in terms of the air pollution impacts, very early on when we developed these data and used them in the Environmental Performance Index, it caught very high-level journalistic, and media interest in the impacts and the levels, partly because countries like China, for instance, had largely not revealed their ground level data, and so people couldn't really understand what the levels of pollution were. A more recent article in 2014 in the New York Times compared Delhi's smog, which is very high compared to Beijing, so sort of set up a dynamic where the two countries and the two cities were being compared in terms of how bad things were. The OECD has created this dashboard for different cities, and so, for instance, in Mexico City, one of the metrics, as you see, is the environment on the lower left in that sort of spider diagram. UNICEF has developed a report on clear air for the children, which heavily relied on these satellite data. And I think one of the greatest impacts of the PM2.5 work was the incorporation in the Global Burden of Disease study, which measures environmental risk factors, and they relied very heavily on the PM2.5 and NO2 data. This is a picture of Matt Hansen from University of Maryland, and he's been using Landsat data to measure deforestation and has received a lot of press attention for its use in the Global Forest Watch, and you can monitor which areas of the world are seeing the steepest deforestation as well as afforestation. They also measure areas where there's forest cover change in improving. The SDG process has also been a big customer for the potential use of remote sensing. I already mentioned PM2.5, and that's being used in Goal 3, Goal 6 on clean water and sanitation. I'll describe some work in that area. Sustainable cities, Goal 11, and life on land. So here's Goal 6, clean water and sanitation. There was a report by UNEP, the World Health Organization, and UN Habitat that looked at the potential of Earth observations to be able to measure certain water quality parameters. The diagram on the left-hand side highlights TRIM, which is a precipitation measurement. GRACE, which is a measure of gravity metric. It's measured groundwater change, has also been used for some indicator development in certain regions where groundwater levels are declining. Urban change for Goal 11 is one of the goals, is looking at how urban areas are changing, and so nighttime lights from VIIRS could be very useful for that. And for land degradation, there's a great deal of interest in the use of satellite data to measure the percentage of land that is degraded over the total area, which is one of the approved indicators. This is non-trivial in terms of what it takes to do that with remote sensing. I like the work of a group called ISRIC in the Netherlands, International Soil Resource Institute, and they have developed some metrics using MODIS data of changes in NPP that are affected by climate and land use, and basically they include rainfall and other parameters that would influence how these brown spots or potential land degradation areas are influenced, but you can see some of those areas highlighted in the circles. So with that, I end my presentation, and I gather, Jennifer, you have some polling questions you want to ask.
I do. Thank you, Alex, and thanks, everybody. What we'll do now is we'll move to the final set of polling questions, and we will give these questions about 2 minutes or so, and then from there we'll move directly to the Q&A portion of the webinar. And we've already do have a few questions, so that's wonderful. All right, everybody, we'll give these about 2 minutes. Thank you. Okay, everybody, we're going to give these just about 30 more seconds, and then we'll move directly to the Q&A period. Okay, everybody, at this point we're going to move to our Q&A period. And just a couple of things I'd like to mention before we dive in with the first question. In the lower right-hand corner of your screen, you'll notice that I've got both the bio, the presentation from today, and the agenda posted. If you highlight any of those files, you'll then be prompted to download those files. And you'll still have an opportunity to do that at the end. You know, we'll leave the virtual meeting space open. If you should think of a question or something, you'll be able to ask that question once we've completed the Q&A period. All right, so our first question, excuse me, for Alex is, will the data products on the PM 2.5 global study be made available on SEDAC?
Well, yeah, so we have already been disseminating the first NASA ROSAS product. Those have been largely superseded by another product developed by the team at Dalhousie University, Aaron von Dankeller and colleagues. And that data set is currently available, and we're about to update that with a new data set which improves on their earlier version and also provides a longer time series. So yes, all of these data are available via SEDAC on our website.
Okay, wonderful. Thank you, Alex. So the next question is, and if you need me to repeat any of it, I can. It's a little bit lengthy. Chlorophyll A studies in the northern Gulf of Mexico, have these studies been related to the summer occurrences of dead zones off the coast of Alabama, Louisiana, and Mississippi, especially as the dead zones results from nutrient runoff, rainfall, etc., across the mid-continent region?
Yeah, well, that was part of our initial intent, and that's why we expected to see much worse declines or increases in chlorophyll concentration in the Gulf of Mexico than we did. Now, again, one of the issues, and this I didn't really address this during the presentation, and this is an opportune time just to say that there are limitations to satellite remote sensing for indicator development. We explore those limitations in much more detail in that Environmental Research Letters publication that I mentioned earlier. One of those limitations is that the time series that you have is limited by the existence of sensors that collect the data. So we could only begin the coastal chlorophyll concentration measure in 1997 when CWIFS, the instrument, was launched. That meant that we were essentially starting our time series in one of the worst El Nino years on record, and that could have influenced the trends in some ways by El Nino typically results in higher ocean temperatures in certain regions of the world. So your chlorophyll concentrations could have been through the roof during that year and then sort of subsided. And that would have been a next step, is to essentially exclude those first years and see if the trends change in any way. And indeed, you know, I'd like to go back to the data and do that just to see, you know, if that changes our conclusions at all. But yes, I mean, the dead zones are there. One of the issues I mentioned earlier is that there are sort of ambient concentrations which may already be high. So if your baseline is very high, any slight increase or slight decrease is not necessarily going to signal either improvement or decline. It just means that you're sort of already in the danger zone, and your trend is moving up or down in that danger zone.
Okay, thank you, Alex. The next question is, have these products been validated in regions like Saharan Africa and South Asia?
Well, you know, ideally what you do is each one of these you have some in situ measurements that allow you to validate the findings. for the air quality, yes, all the data that we disseminate have had some ground level validation, particularly the ones from Dalhousie University. The biomass burning, the NASA team that develops the GFED4 database has done a lot of validation work, and they're very careful. The coastal water quality is more difficult, and there's simply less ground-based, or I should say ocean-based data that are collected over long terms on ocean color or chlorophyll concentrations, and they vary heavily over space and time. So you really need a long-term monitoring in order to in situ monitoring in order to validate those. As far as Africa goes, those are the regions. It's one of the regions that's frankly the least monitored and has some of the biggest in situ gaps in measurements. So no, I would say that a good deal of Africa has had less validation than the rest of the world.
Okay, thank you, Alex. Let me get to the next question here. For the map viewer, they are all linked but not resampled to have the same pixel size, and they don't seem to have a scale which might be helpful to differentiate nominal scale pixel size in meters.
Yeah, that's a good point. I mean, the purpose of the mapping tool is really to do a first cut view of the data, and we view it as a service to our users to provide a view of the data before they might decide to download and integrate the data in their own applications. They're also all available via WMS, so anyone with a OGC compliant map service can bring those services into their own mappers. The scale bar, I haven't checked. I think, let me just double check. We could do better with that as far as providing scaling. And I agree that, there are different pixel sizes, and that's the kind of thing that you need to dig into the metadata and the documentation for each of these data sets to find out what the resolution is.
Okay, thank you, Alex. So the next question here, let's see, just give me one moment. Okay, the next question is, what resources are available to policymakers with respect to interpreting and applying the product?
Yeah, so that was kind of the bridge we didn't eventually cross with the NASA ROSES project. We were interested to see whether these indicators could be of use, but we didn't actually apply them. The EPI report, which is the Environmental Performance Index report, which we produce on a biannual basis. So the last one was in 2016, released in January, provides more guidance to policymakers about how these data or these indicators should be interpreted, and also a bit more information about uncertainties in the data and things of that sort. But I agree, and I think it's a great question. Just putting things over the transom, as it were, putting indicators out there does not guarantee that they'll be used in an intelligent manner, and a lot of work needs to be done in order to ensure that policymakers are interpreting the results correctly.
Okay, thank you, Alex. The next question is, with respect to air quality for public health, particulate matter finer than 2.5 is of interest as it is highly toxic. Are you aware of any sensor that can measure finer particulate in the near future?
Honestly, I'm not aware if there's particulate. Obviously, there's finer particulate matter than 2.5, but I don't really know if there's some effort out there to measure that at a higher level. Really the world has sort of woken up to the fact that PM10 is not good enough, and that was really the standard bearer for up until the late 90s, early 2000s. And some countries still have a very incomplete network of ground-based PM2.5 sensors, so I'm not aware of any effort to try to push that to even higher or smaller particles.
Okay, thank you. Our next question is, would it be possible to replicate some of these studies, specifically land surface temperature, derivation, and burnt area using Landsat and hence get finer edges slightly less exaggerated.
Could you repeat that last part?
Okay, so let's see. Specifically, land surface temperature derivation and burnt area using Landsat and hence get finer edges / slightly less exaggerated.
Well, I mean, all of these can be, you're limited by the sensor resolution, so you could go as high with the burn area as the 500-meter native MODIS product. For various reasons, they chose to disseminate the data at lower resolution because they're integrating a number of things in a model to produce the emissions estimates. But yes, people who want to do this work at higher resolution can download the raw data and process them themselves, and I think that there may be some guidance using the peer-reviewed publications that are behind GFED for doing that. And the same goes, I think our particulate matter grids are at 1 kilometer, which is fairly high resolution, but in theory you could get higher resolution measurements using higher resolution sensors.
Okay, thank you, Alex. Our next question is, are there prospects for detecting toxics in air or water from satellite remote sensing?
No, we have done something. We produced actually a journal article working with a number of experts. I think it's in the Journal of Atmospheric Research. In any case, that's by Angel Su, HSU, and a number of co-authors. And we looked at this whole question of what could be measured using satellite data. Toxics is not one of the parameters that can be measured easily using remote sensing, unfortunately.
Okay, thank you, Alex. Okay, the next question is, satellite remote sensing can make a significant contribution to monitoring water quality. There are projects or programs to apply similar studies that you showed on coastal areas to inland water bodies, to monitor inland water bodies?
Yeah, I think some of the larger inland water bodies can be monitored using remote sensing. There are some limitations in terms of the sensor resolution to pick up smaller water bodies. There are also issues with bottom reflectance, and typically that's not a big issue if you're measuring trends because in theory the bottom reflectance should remain fairly constant, but you know, any work that you do in the near coastal zone or in lakes will be influenced by the fact that the ocean color sensor is picking up bottom reflectance as well as we say it, gunk in the water.
And I just wanted to add that the NASA Applied Sciences RSET program has held webinars on water quality. So Christina, I can send you a link to some of those webinars. And then the next question is, let's see, are there any plans to include other NASA data from other DACs into the map viewer?
Well, we are working very closely with the Earthdata team at NASA Goddard, and they produced something called I'm apologizing. Jennifer, you may be able to help me out.
NASA Worldview?
Worldview. I was going to say Worldview, and I suddenly caught myself thinking it might be something else. But Worldview is a very nice and very slick interface for viewing near real-time satellite data, and we also provide a number of these data layers in that tool. So if you want to see our data and some of the satellite data as well alongside these real-time data on, say, active fires or aerosol optical depth, you know, you can see where dust storms are coming or where fires are burning and then see the smoke that's being generated by those fires. That's a good place, a good tool to use for that.
And thank you, Alex. And what I've done, I've typed the URL for NASA Worldview into the Q&A pod. And one of their newer features for that specific application now is to be able to create data animation, so you could actually take a look at how things have changed over time with some of your data layers. So the next question is, how appropriate is the study of mountain ecosystems, or how appropriate can that be by using these products?
Well, one of the beauties of satellite data is you can slice and dice according to your particular region, ecosystem of interest. And so one of the things we wanted to do for forest burning, for instance, is see, are there trends in boreal forests that are somehow masked by looking at the country level? So if you wanted to look at all boreal forests around the world, you could easily do that in a GIS environment, processing the data in such a way that you're simply looking at trends in those boreal forests or in mountain zones, you name it. So that's really one of the beauties of the satellite data and the gridded data, is you can really choose your area of focus.
Okay, thank you, Alex. Our next question is actually a follow-on to the earlier question regarding sub-Saharan Africa. Does it mean that these techniques are not appropriate for Africa since the products have not been validated in Africa?
No, I would not say that. There's maybe less ground level validation but in Africa, but there are, the models have been validated in other regions. So I have not been told by the team that developed the particulate matter grids, for instance, that there's any reason to question their validity in Africa. There are issues in parts of Africa, though, and anywhere in the tropics with cloud cover, and that can affect the ability of satellites to retrieve these parameters. And so it's something to be aware of, is that in some regions you may have a lower density of samples to draw on than you do in other areas, owing to cloud cover.
Okay, thank you, Alex. The next question is, there are only 2 videos on the YouTube SEDAC YouTube channel. Is this channel not for dissemination? If not, where else on YouTube? And I did provide an answer to this participant that there are many webinars that we have housed from SEDAC and the other 11 DACs on our NASA Earthdata YouTube channel, including information about the gridded population of the world version 4 data product, some of their web mapping tools, and so that's an additional location to check out. But then I defer to you, Alex, if you have further comments on this.
Well, we'll certainly be putting the link to this presentation on our website, and we have another one in the pipeline. So that's another SEDAC video that's in the pipeline.
And the other thing is, for this participant, YouTube will not allow the same video to be posted in 2 locations. So generally for all of the Earthdata webinars, those are posted on our NASA Earthdata YouTube channel. If it's posted in 2 locations, the second video can be removed. So that's one something to keep in mind. All right. So the next question is, what is your relationship with policy or decision makers regarding the use of these data sets to inform policy?
Well, some of our, some of it is, it's a good question. Some of that is anecdotal. We hear about the influence that these indicators have had in discussions among policymakers. We have governments, environment ministries reaching out to us periodically to discuss how we generate some of these data sets and indicators, and maybe to explain in some cases why the indicator seems to be telling a story different from what they may be using in their own country. And we have more recently done some work on another NASA ROSES project on urban heat islands in Philadelphia and New York City, and we had in that project and that was using satellite data, again, MODIS, land surface temperature, as one of the parameters to measure the urban heat island in these cities. And we had direct conversations with policymakers about the utility of those data and how they reflect changes. And some of the changes we saw in land surface temperature, frankly, had to do with, obvious developments that occurred at the city level, like either new parks where cooling was occurring, or new developments such as shopping malls and parking lots where there was a decided increase in the urban heat island or surface temperature. So they prompted a lot of very useful discussions, and I think presented a really unique and useful view for the policymakers we engaged with.
Okay, thank you, Alex. I just want to let everybody know that we've only got 5 more minutes left to the Q&A extended period here. And at that point, when we're finished, we'll leave the virtual meeting space open. If you think of any questions, and you may certainly email me, and I can forward those questions along to our speaker this afternoon. The next question is regarding air quality. Is 1 year the minimum temporal aggregation window to obtain a reliable product, or could eventually monthly or daily observations used for near real-time monitoring applications, provided cloud-free data are available?
The team at Dalhousie has advised us that longer time periods are generally better because you average out some of the noise that may be in the data, or the peaks and valleys. I think that a monthly composite would work if I interpret their methodology correctly. I don't think they'd recommend daily views, and for the reasons I mentioned.
Okay, thank you, Alex. Our next question is, are there any indicators to monitor plant health with respect to plant diseases?
Yeah, we haven't tried that, but certainly I was actually interested in using, I believe it's OCO, or now I'm going to forget which sensor it is that looks at photosynthesis. And, certainly things like the pine bark beetle in the Rocky Mountain states and other pest infestations do leave a noticeable signature in remote sensing. Declines in NDVI relative to prior years, things like that. And so I do believe there's a significant potential to use remote sensing to track those. They're already being used, but you could develop policy-relevant metrics that would help policymakers see how these pest infestations are affecting the plants in given regions.
So I think there are actually some MODIS data products. There's certainly a leaf area index, and then I think it's, the FPAR MODIS, am I saying that correctly, available through our Land Processes Distributed Active Archive Center. There's also a really great subsetting tool available through the Oak Ridge DAC, so I can follow up with this end user separately offline with additional resources.
Great.
Look at vegetation indices, etc. Okay, are there any further questions? We have a couple of minutes left for the Q&A period. Anybody? Okay, here we are. Do you use glacial displacement data for SEDAC graphics?
We haven't tried that. If that, by that it means, shrinking glaciers. We have not tried that. I would suggest going to the National Snow and Ice Data Center, because they have a very nice data collection around glacial extent.
Yes, and I've included the URL for NSIDC. That's nsidc.org. All right, well, if there are no further questions, everybody, what we'll do at this point is we will log off from the telecon portion of the webinar. Again, I'll leave the virtual meeting space open until 11:30 a.m. Eastern Time, so that's about 15 minutes. If you think of any questions, or if you're interested in downloading the files, again, those are located in the lower right-hand corner. Okay, so the links to the slides. So for this user, does everybody see in the lower right-hand corner there's a file sharing pod, and it has a title, Environmental Indicators, And if you were to click on the, I hope I'm interpreting this correctly, if you were to click on, for example, the file that has, this is the largest file, it's 27 megabytes, Earthdata webinar satellite indicators, you would be prompted to download that file. Does that make sense, Holly? Okay, great. And then just another note, even after the 15 minutes are up, once you access the recording for this webinar online at our online Adobe Connect catalog, which you'll find by going to tinyurl.com, Earthdata webinar, you'll be able, it's a persistent feature, so you would still be able to download any of the files from any of the webinars dating back actually to 2013, so you could kind of search around and find some additional SEDAC webinars just by clicking on, going to the end and doing the same thing, clicking within the file share pod, highlighting a file, and download. All right, well, thanks everybody for joining us today. Thanks to our speaker, and we hope to see you again at an upcoming webinar. At this point, we will log off from the telecon. All right, thanks everybody. Thanks, Alex.
Thank you. Bye, everybody.
Bye-bye now.